The National Electrical Code, or NEC, does require an equipment grounding conductor, or EC, to be installed with a feeder that is run between structures. NEC Section 250.118.7 states that where a service or feeder is run underground, all metallic raceways, cables, or other equipment shall have an equipment grounding conductor installed. The lack of a neutral and ground between structures creates a problem with tripping the breaker in a ground fault condition. Without a neutral path, there is no complete circuit for current to flow, and the breaker will not trip. Without an equipment ground, there is no low impedance path for fault current to flow, and the overcurrent device may not operate properly. The NEC does not explicitly require an equipment ground in the scenario you describe, but it does require an equipment ground in general for underground feeders. NEC Section 250.118.7, as cited above, applies to all underground feeders, regardless of whether they have a neutral or ground. In this situation, the best solution is to install an equipment grounding conductor, or EC, along with the feeder in the PVC conduit. This will provide a low impedance path for fault current to flow, ensuring that the overcurrent device will operate properly in a ground fault condition. Do not bond the fire alarm shield in the conduit between the structures. Bonding the shield would create a parallel path for fault current, which could result in nuisance tripping of the overcurrent device. The shield should be insulated at both structures, per the manufacturer's recommendation. Let's delve deeper into the specifics of equipment grounding conductors and their crucial role in electrical systems, especially when dealing with separate structures. Firstly, let's define what an equipment grounding conductor, or EC, is. It's a conductor that provides a low impedance path for fault current to return to the source. This path is essential for the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, during a ground fault. Without a properly sized and installed EGC, fault current may not be high enough to trip the breaker, leading to potential hazards like electrical shock, fire, and equipment damage. Now consider a scenario where a 480-volt 3-wire system without a neutral feeds a separate structure. The absence of both a neutral and an equipment grounding conductor presents a significant challenge in ensuring effective ground fault protection. In a typical grounded system, the neutral conductor provides a return path for unbalanced currents and also serves as a reference point for voltage stabilization. However, in a delta-connected system without a neutral, the equipment grounding conductor becomes even more critical. It acts as the primary path for fault current to return to the source in the event of a ground fault. The NEC mandates the installation of an EGC with feeders that run between structures, particularly when they are underground. This requirement is rooted in the need to maintain a safe and reliable electrical system. The specific NEC section that addresses this is 250.118.7, which we previously mentioned. Now, let's address the concern regarding the lack of a low impedance path to trip the breaker in a ground fault condition when neither a neutral nor a ground is present. This concern is valid. Without a dedicated EGC, the fault current may have to find its way back to the source through other unintended paths, such as metallic conduits, building steel, or even the earth itself. These paths typically have a much higher impedance than a properly sized EGC, which limits the magnitude of the fault current. As a result, the overcurrent protective device may not trip quickly enough, or at all, to clear the fault. This prolonged fault condition can lead to overheating of conductors, insulation breakdown, and ultimately, an electrical fire. To mitigate this risk, the NEC requires the installation of an EGC sized according to NEC Table 250.122, based on the rating of the overcurrent protective device protecting the feeder. This table provides guidelines for selecting the appropriate size of the EGC to ensure that it can effectively carry the available fault current. Now consider the situation involving the fire alarm system and the nuisance alarms caused by potential differences between the two structures. This is a common issue when dealing with interconnected systems that are supplied from different power sources. The potential difference between the structures can create circulating currents in the fire alarm system's wiring, leading to false alarms. Bonding the shield of the fire alarm cable of both structures, as was initially done, can sometimes alleviate this problem by providing a common reference point for the two systems. However, this practice can also create a parallel path for fault current, which, as we have already discussed, can have undesirable consequences. The fire alarm equipment manufacturer's recommendation to insulate the shield everywhere except at the main fire alarm control panel is based on the need to isolate the fire alarm system from potential ground loops and circulating currents. This approach helps to prevent nuisance alarms and ensures the reliable operation of the fire alarm system. Installing a bond conductor in the fire alarm conduit to isolate the shield, while seemingly a viable option, is generally not recommended. This is because it can create a hidden parallel path for fault current, which can compromise the integrity of the equipment grounding system. Furthermore, it may violate the fire alarm system manufacturer's instructions and could void the warranty. The preferred approach is to address the potential difference between the structures by installing a properly sized equipment grounding conductor with a feeder as required by the NEC. This will help to equalize the ground potential between the two structures and reduce the likelihood of circulating currents in the fire alarm system. In addition to installing an EGC, it may also be necessary to implement other bonding and grounding techniques such as bonding metallic conduits and equipment enclosures to the EGC. This will help to create a lower impedance path for fault current and ensure that all metallic parts are at the same potential. It's important to consult with a qualified electrical engineer or electrician to determine the best course of action for your specific situation. They can assess the electrical system, identify potential grounding and bonding issues, and recommend solutions that comply with the NEC and other applicable codes and standards. In summary, the NEC requires an equipment grounding conductor to be installed with feeders that run between structures, especially when they are underground. This requirement is essential for ensuring the safe and reliable operation of the electrical system and for protecting against electrical shock, fire, and equipment damage. Do not bond the fire alarm shield in the conduit between the structures, as this can create a parallel path for fault current and compromise the integrity of the equipment grounding system. Instead, follow the fire alarm system manufacturer's recommendations and consult with a qualified electrical professional to address any grounding and bonding issues. Now, let's further elaborate on the importance of a low impedance ground fault path. The effectiveness of a grounding system hinges on its ability to provide a lower impedance path for fault current. Impedance, measured in ohms, is the total opposition to current flow in an alternating current circuit. It includes resistance, which is the opposition to current flow in a direct current circuit, and reactance, which is the opposition to current flow due to inductance and capacitance. A high impedance ground fault path can significantly reduce the magnitude of fault current, delaying or preventing the operation of overcurrent protective devices. This delay can lead to dangerous conditions such as sustained arcing faults, which can generate intense heat and ignite nearby combustible materials. To ensure a low impedance ground fault path, several factors must be considered. Firstly, the size of the equipment grounding conductor must be adequate to carry the available fault current. NEC Table 250.122 provides guidance on selecting the appropriate size of the EGC based on the rating of the overcurrent protective device. Secondly, the connections between the EGC and other metallic parts such as conduits, enclosures, and equipment frames must be clean, tight, and free of corrosion. Loose or corroded connections can significantly increase the impedance of the ground fault path. Thirdly, the length of the EGC should be kept as short as possible to minimize impedance. Long EGC runs can increase impedance due to the inductive reactance of the conductor. In addition to these factors, the type of grounding electrode used can also affect the impedance of the ground fault path. A grounding electrode is a conductive object such as a ground rod, ground plate, or underground metallic water pipe that is used to establish a connection to the earth. The NEC requires that all grounding electrodes have a resistance to ground of 25 ohms or less. If the resistance to ground exceeds 25 ohms, a supplemental grounding electrode must be installed. Choice of grounding electrode depends on the soil conditions and the available space. Ground rods are the most common type of grounding electrode, but ground plates and underground metallic water pipes may be used in certain situations. It's important to ensure that the grounding electrode is properly installed and maintained to provide a low impedance connection to the earth. Now let's consider the specific case of a 480-volt, 3-wire system without a neutral. In this type of system, the equipment grounding conductor is even more critical because it is the only path for fault current to return to the source in the event of a ground fault. Without a neutral conductor to provide a low impedance return path, the EGC must be sized and installed to handle the full available fault current. The NEC requires that the EGC be sized based on the rating of the overcurrent protective device protecting the feeder, as specified in NEC Table 250.122. In addition to sizing the EGC properly, it's also important to ensure that all metallic parts are effectively bonded to the EGC. This includes conduits, enclosures, equipment frames, and any other metallic parts that could become energized in the event of a ground fault. Bonding is the process of connecting metallic parts together to create a low impedance path for fault current. Bonding can be achieved by using bonding jumpers, bonding bushings, or other approved methods. The NEC provides detailed requirements for bonding in Article 250. By effectively bonding all metallic parts to the EGC, you can ensure that fault current will have a low impedance path to return to the source, causing the overcurrent protective device to trip quickly and clear the fault. In summary, a low impedance ground fault path is essential for the safe and reliable operation of electrical systems. To ensure a low impedance ground fault path, it's important to size the equipment grounding conductor properly, maintain clean and tight connections, keep the EGC run short, and use an effective grounding electrode. In 480-volt, 3-wire systems without a neutral, the EGC is even more critical because it is the only path for fault current to return to the source. By following the NEC requirements for grounding and bonding, you can minimize the risk of electrical shock, fire, and equipment damage. Let's elaborate further on the practical implications of NEC Article 250 and its relevance to equipment grounding, especially in the context of interconnected structures and fire alarm systems. NEC Article 250 is the cornerstone of electrical safety, providing comprehensive guidelines for grounding and bonding of electrical systems. Its primary objective is to create a low impedance path for fault current, ensuring that overcurrent protective devices operate promptly in the event of a ground fault. This rapid clearing of faults minimizes the risk of electrical shock, fire, and equipment damage. Within Article 250, several sections are particularly relevant to the scenario we are discussing. Section 250.4 emphasizes the importance of effectively grounding electrical equipment to minimize voltage to ground during normal operation and to limit the voltage rise on equipment enclosures during a ground fault. This section underscores the need for a robust equipment grounding system that can quickly dissipate fault current. Section 250.96 addresses the bonding of metallic parts, including conduits, enclosures, and equipment frames. It mandates that these parts be bonded together to create a low impedance path for fault current. This bonding is typically achieved using bonding jumpers, bonding bushings, or other approved methods. The size of the bonding jumper is determined by NEC Table 250.102, based on the size of the ungrounded conductors. Section 250.118 specifies the types of conductors that are permitted to be used as equipment grounding conductors. These include copper, aluminum, and copper-clad aluminum conductors. The EGC can be either bare or insulated, but if insulated, it must have a green or green with yellow stripe insulation. The size of the EGC is determined by NEC Table 250.122. Based on the rating of the overcurrent protective device protecting the circuit. Now, let's consider the specific challenges posed by interconnected structures and fire alarm systems. When multiple structures are supplied from different power sources, potential differences can exist between the grounding systems of each structure. These potential differences can create circulating currents in the interconnected systems, leading to nuisance alarms and other problems. To mitigate these issues, it's essential to establish a common grounding system between the structures. This can be achieved by installing a grounding electrode system at each structure and interconnecting them with a grounding electrode conductor. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. In addition to establishing a common grounding system, it's also important to bond all metallic parts of the interconnected systems together. This includes conduits, enclosures, equipment frames, and any other metallic parts that could become energized in the event of a ground fault. Bonding helps to equalize the ground potential between the structures and reduce the likelihood of circulating currents. When dealing with fire alarm systems, it's crucial to follow the manufacturer's recommendations for grounding and bonding. Fire alarm systems are often sensitive to electrical noise and interference, and improper grounding can lead to false alarms and other malfunctions. The fire alarm system manufacturer typically provides detailed instructions on how to ground and bond the system to minimize these issues. In general, it's best to isolate the fire alarm system from the building's grounding system to prevent ground loops. This can be achieved by using isolation transformers or by grounding the fire alarm system at a single point. The fire alarm system's wiring should also be shielded to minimize electrical noise and interference. The shield should be grounded at the fire alarm control panel, but it should be insulated from ground at all other points. Finally, it's important to test the grounding system regularly to ensure that it is functioning properly. This can be done by measuring the resistance to ground of the grounding electrodes and by verifying that all metallic parts are effectively bonded together. In summary, NEC Article 250 provides comprehensive guidelines for grounding and bonding of electrical systems. By following these guidelines, you can ensure that your electrical system is safe and reliable. When dealing with interconnected structures and fire alarm systems, it's essential to establish a common grounding system, bond all metallic parts together, and follow the manufacturer's recommendations for grounding and bonding. Regular testing of the grounding system is also important to ensure that it is functioning properly. Now, let's delve deeper into the nuances of fault current and its behavior in grounded and ungrounded systems, further solidifying our understanding of the critical role played by the equipment grounding conductor. Fault current is the current that flows in an electrical circuit during a fault condition such as a short circuit or a ground fault. The magnitude of fault current depends on several factors, including the voltage of the system, the impedance of the circuit, and the location of the fault. In a grounded system, a ground fault occurs when an ungrounded conductor comes into contact with a grounded surface, such as a metallic enclosure or a grounding electrode. Fault current flows from the ungrounded conductor through the grounded surface and back to the source through the equipment grounding conductor. The equipment grounding conductor provides a low impedance path for fault current, allowing the overcurrent protective device to trip quickly and clear the fault. In an ungrounded system, a ground fault can occur without immediately causing a disruption of service. This is because there is no intentional connection to ground, so the fault current is limited by the capacitance of the system. However, an ungrounded system is not necessarily safer than a grounded system. In fact, an ungrounded system can be more dangerous because a second ground fault on a different phase can create a short circuit, resulting in a high fault current and a potential fire hazard. Furthermore, an ungrounded system can be more difficult to troubleshoot because the fault current is often small and difficult to detect. To address these issues, the NEC requires that ungrounded systems be equipped with ground detectors. Ground detectors are devices that monitor the voltage between each phase and ground. When a ground fault occurs, the ground detector will alarm, alerting personnel to the fault condition. The NEC also requires that ungrounded systems be equipped with overcurrent protective devices that will trip in the event of a second ground fault. The size and type of overcurrent protective device depends on the voltage and current rating of the system. In both grounded and ungrounded systems, the equipment grounding conductor plays a critical role in ensuring safety. The equipment grounding conductor provides a low impedance path for fault current, allowing the overcurrent protective device to trip quickly and clear the fault. Without an equipment grounding conductor, the fault current may have to find its way back to the source through other unintended paths such as metallic conduits, building steel, or even the earth itself. These paths typically have a much higher impedance than a properly sized equipment grounding conductor, which limits the magnitude of the fault current. As a result, the overcurrent protective device may not trip quickly enough, or at all, to clear the fault. This prolonged fault condition can lead to overheating of conductors, insulation breakdown, and ultimately, an electrical fire. In summary, fault current is the current that flows in an electrical circuit during a fault condition. The magnitude of fault current depends on several factors, including the voltage of the system, the impedance of the circuit, and the location of the fault. In a grounded system, the equipment grounding conductor provides a low impedance path for fault current, allowing the overcurrent protective device to trip quickly and clear the fault. In an ungrounded system, a ground fault can occur without immediately causing a disruption of service, but a second ground fault can create a short circuit, resulting in a high fault current and a potential fire hazard. The NEC requires that ungrounded systems be equipped with ground detectors and overcurrent protective devices to mitigate these risks. In both grounded and ungrounded systems, the equipment grounding conductor plays a critical role in ensuring safety. Now, let's expand on the practical considerations for installing and maintaining equipment grounding conductors, with a particular focus on the challenges and best practices for ensuring reliable grounding in diverse environments. The proper installation and maintenance of equipment grounding conductors, or EGs, are paramount to ensuring the safety and reliability of electrical systems. While NEC Article 250 provides comprehensive guidelines, practical considerations often dictate the most effective approach in specific situations. One key consideration is the environment in which the EGC is installed. In corrosive environments, such as those with high humidity, salt spray, or chemical exposure, special precautions must be taken to protect the EGC from corrosion. This may involve using corrosion-resistant materials such as copper or stainless steel, or applying a protective coating to the EGC. The connections between the EGC and other metallic parts must also be protected from corrosion. This can be achieved by using corrosion-inhibiting compounds or by encapsulating the connections in a waterproof sealant. Another important consideration is the mechanical protection of the EGC. In areas where the EGC is subject to physical damage, such as from impact or abrasion, it must be protected by a conduit, raceway, or other approved means. The conduit or raceway must be securely fastened to the EGC to prevent it from being pulled loose. The EGC must also be protected from overcurrent. This can be achieved by sizing the EGC to carry the available fault current and by installing an overcurrent protective device in the circuit. The overcurrent protective device must be sized to protect the EGC from overheating. The EGC must be installed in a neat and workmanlike manner. This means that it must be properly supported, secured, and terminated. The EGC must not be spliced or jointed unless it is done in an approved manner. The EGC must be accessible for inspection and maintenance. This means that it must not be concealed behind walls, floors, or ceilings. The EGC must be properly labeled. This helps to identify the EGC and ensures that it is not inadvertently disconnected or damaged. Regular inspection and maintenance of the EGC are essential to ensure that it is functioning properly. The EGC should be inspected for signs of corrosion, damage, or loose connections. Any defect should be repaired promptly. The resistance to ground of the grounding electrode should be measured periodically to ensure that it is within acceptable limits. If the resistance to ground is too high, the grounding electrode should be replaced or supplemented. The bonding connections should be inspected to ensure that they are tight and free of corrosion. Any loose or corroded connections should be tightened or replaced. The overcurrent protective device should be tested to ensure that it is functioning properly. If the overcurrent protective device is not functioning properly, it should be replaced. In addition to these practical considerations, it's also important to be aware of the potential hazards associated with working on electrical systems. Only qualified personnel should perform electrical work. All electrical work should be performed with the power off. Proper personal protective equipment, or PPE should be worn when working on electrical systems. Lockout-tagout procedures should be followed to prevent accidental energization of the system. In summary, the proper installation and maintenance of equipment grounding conductors are paramount to ensuring the safety and reliability of electrical systems. Practical considerations often dictate the most effective approach in specific situations. By following these guidelines, you can minimize the risk of electrical shock, fire, and equipment damage.